You might have seen a few differential equations at this point, and some of them probably look something like this. Or maybe this? I want to look at these kinds of equations, specifically differential equations in this form. The full name for these is linear first-order ordinary differential equations, but we won't be saying all of that today, don't worry. Now, we can do lots of things with these differential equations, but I want to focus on solving them in particular. That is, I want to focus on finding a function, y, in terms of x, that solves this equation. Let's try doing that. First, I noticed that the left side of this equation looks kind of like the product rule. Almost. It's two terms, one of which is a product, with one getting a derivative of a particular function. Let's focus on where it doesn't quite match up. Since the left term gets the derivative of y, the right term should get the derivative of our other function. But p of x isn't really the derivative of anything necessarily. It's just some function of x. It's probably not the derivative of 1. So, let's make a modification to the equation. I want to do something to this equation that will make the thing multiplied to y the derivative of the thing multiplied to y prime. An easy way to modify both terms at once would be to use multiplication. Let's multiply something on both sides of the equation. Call it I. Doing that means that the derivative of I should be I times p of x. We need I to be some kind of function whose derivative is just itself times p of x. Pause now if you want to think about it, because you know a function that can do something like this. E to the x turns into itself when you take its derivative, and the chain rule makes e to the f of x have a factor of f prime of x in its derivative. So, if we want p of x to be a factor instead, we'll need its antiderivative in the exponent. This brings us to a really nice conclusion. I always equals e to the power of the integral of p of x. We call that the equation's integrating factor. You integrate p of x, slap that onto the exponent of an e, and you multiply the resulting function to the entire equation. This automatically, no matter what, results in the product rule being present on the left side. Now, how is that actually useful, though? Are we just rewriting this for fun, making derivatives appear? This actually does do something for us, promise. Since it's the result of the product rule, we can reverse it. The product rule is just an equation, after all. So, we get this. And since we're trying to solve for y, it'd probably be best to break it out of that derivative, which, you might recall, we can do with an integral. So, we integrate both sides and end up here. All we have to do now is divide by that same integrating factor, and we're done. Let's try this on, an actual problem, real quick. Let's say this equation right here. Sometimes you'll have to rewrite the equation to more accurately match the formula. There are some weird steps here, so feel free to pause and make sure you understand everything. When doing this with actual equations, often people just skip the middle parts and memorize the end result instead. That is, get the integrating factor, integrate its product with the opposite side, and divide the result by the same integrating factor. I like to write the product rule though, so you'll probably catch me writing it all. Keep in mind though that since the numerator has an indefinite integral, it'll have plus c. So sometimes you'll see the answers written as two fractions. That should be all you need for integrating factors. Bye!